Hello everyone, I hope this finds you well. We're going to continue on with ocean movement in Unit 6, talking about waves still. We're going to talk specifically about the circulation of water on the Earth. And so water moves not only around the Earth, but it also moves from the surface to the sea floor and back again. And there's two ways that water does that. One's called upwellings. That's where water comes up to the surface from the deep. Water that's in an upwelling is very rich in nutrients. That's because everything that dies technically falls to the ocean floor. And so that water that's carried up to the surface is going to be very rich in that kind of dead material, which a lot of ocean life eats. But it's going to be very poor in oxygen because down deep below, there's not going to be a lot of ways for oxygen to get down that deep. So the water coming up is going to be very oxygen poor. The other way that water circulates is called a downwelling. And that's when water falls from the surface down to the deep parts of the ocean or down toward the ocean floor. That water is going to be very rich in oxygen because it was at the surface and oxygen is going to diffuse into the water very easily. However, nutrients are going to be very poor because obviously when everything dies, it falls to the ocean floor. So this is a way for the ocean to kind of stir or mix things around so that organisms can get oxygen, but they can also get nutrients because of the way that the water moves. It allows those two vital, important things for life to get to areas that they might be poor in. Waves, we said before, comes from friction of the wind on the surface of the water, and that moves water molecules a very, very short distance. Most of the time when we think of waves, we think of water moving long distances, but actually water molecules stay kind of in their same area for the majority of their, if you will, for lack of a better word, life cycle. As it falls, as that water molecule falls, it forces other water molecules to move, and that's what starts creating waves. So before we get too far into how waves are created, let's talk about the anatomy of a wave. What are the parts of a wave, or what does a wave actually look like? And so in this diagram, we have listed out several parts. The very top of a wave is called the crest. If you look right there at the top of A and B, that would be the crest. If you're looking at the wave, notice there's a dotted line. That would be a very calm sea. So you're going from zero to the very top of a wave. That would be the crest. Or if you go from zero, which is the sea level, down to a wave, that would be the wave's trough. From the calm sea level to the crest, that distance from zero to the crest is called the wave height. And then if you measure from wave A to wave B, that's called a wavelength. From crest to crest would be a wavelength. When we talk about wave frequency, that's the number of wave crests that pass a point every second. So if you had point A out there, how many waves would cross that in 1 second? That would be your wave frequency. And then a wave period is the time required for the wave crest to get from point A to point B. So the full wavelength, that time that it takes, would be the wave period. So you should have had a handout from Google Classroom that talked about the anatomy of a wave. You're welcome to pause this video and fill out that handout so that you know the parts of a wave. Rip currents or rip tides are something I always briefly talk about when we talk about waves and tides and currents. Basically, a rip current is what's called a backflow from the beach. So a wave comes into the beach, But then, of course, waves go back out into the ocean. And occasionally that back and forth creates a current that literally can pull things back out into the ocean and actually can pull you under the surface of the ocean. And so the only way to get out of a rip current or a rip tide is to swim parallel to the shore, because if you try to swim back toward the shore, the current is going to continue to pull you out or even pull you under. And then, of course, swimming away from the shore is going to just put you further and further out into the ocean. So the only way of escape is going parallel to the shore or parallel to the rip current so that you can get out of that current and get away from it. Okay, so let's talk about wave energy and how waves are made. So as I said before, a molecule of water gets moved, and the energy of that wave is transferred to the next wave or transferred to the next water molecule. The water molecules don't actually move. If you look at the diagram here, they actually just go in a circle. And what they do is they move the water molecules next to them and transfer their energy to the next water molecule. So grab your book and turn to page 108. Down at the very bottom, there is a diagram of this same thing that talks about how it moves that energy from one molecule to the next. Notice it doesn't really move very far. It just stays in one spot, and it moves its energy in a circular motion to the next water molecule. So technically, water molecules stay relatively in the same place. They just transfer their energy, is what you need to take away from this. Also on page 109 is a really good diagram of a wave, if you still need that for the handout to finish that up. Okay, breakers. A lot of times you'll hear the word breakers used for surfers. Breakers are just basically when a wave reaches a certain height and it's moving faster than its base, because a wave has a top or a crest and it also has a base. And if the crest is moving faster than the base, then it's going to kind of fall over on itself. And we see those big, huge waves a lot of times. I think Hawaii has them, sometimes in California. And those are the big breakers that everybody wants to use when you go surfing. Well, the way that they work is that the closer you get to the shore, the energy gets pushed upward, because the water gets shallower and shallower, but it still has the same amount of energy. And we know from Newton's law that energy doesn't just dissipate, right? It just doesn't go into the air. So instead of the energy pushing the next wave so much, or the next water molecule, it pushes the water molecules up, making the wave higher and higher and higher. And if the crest is moving faster than the base, which is touching technically the seabed or the shoreline, that's going to slow it down, right, due to friction. Then it's going to kind of fall over, if you will, the top of the wave and create what's called a breaker. So that's how you get a breaker. A lot of surfers love those breakers, especially the big ones. They can get out there and ride those, and the whole point is you want to get on top of the crest and stay on top of the crest and ride that extra energy as long as you possibly can. Or even sometimes they get inside of the breakers as they fall over and ride that energy as far as you can on your surfboard. Now, a tsunami is kind of the same concept, if you will. A tsunami, remember, comes from an earthquake that happens either out in the ocean or very near to the ocean, and creates a large wave out in the ocean. Well, tsunami waves aren't really a big deal until they start coming close to shore. If you were out on the ocean somewhere in a ship, you probably would not notice the tsunami wave itself, because it's not going to be very big. But if you notice from our diagram here, again, as you get closer to shore, that the base of that wave starts creating friction at the base of it, but the crest is still moving at a really rapid pace. And so you start to get this huge wave. And when I say huge, I'm talking 15, 20, even I've heard some even 30 feet high waves that come into shore, and they build and build and build until they reach really, really big heights, and they come crashing down into inland. And they can go very, very far inland, actually, and do a lot of destruction on housing and people and that kind of thing. Most of the time, what you'll see right before a tsunami wave hits, the bottom base where the ocean is will literally retract back out into the ocean. And basically what it's doing is it's got so much energy, it's sucking the water back out so that it can build the wave bigger and bigger, because there's so much energy behind it because of the earthquake. And then that big wave will come in and it will crash over the ocean, or over the village or the city or whatever is there on the shoreline. And that's when it becomes really, really dangerous, because a lot of people, they will see the water retract and they want to walk out into the ocean base where they've never been able to walk before. And that is no bueno, not a good idea, because that's when you know this big tsunami is coming, and a lot of people will lose their lives that way. So notice that this wave comes in, and it's a big, huge breaker that comes in, and it's many times taller, a lot of times, than buildings and things. And even if it's not taller, it's got a lot of energy behind it, so it can move things like houses and cars, etc. And I think if you recall from the past, we've seen videos where that tsunami wave has come in, and it can move a lot of debris. So that's kind of a scary thing. And that is the end of our PowerPoint for today.